I did case study 3, which was talking about exploring steady-state error to solely eliminate it after a few trials for this submarine. So first we're starting by showing case A, which basically just needed to simplify this block diagram that I showed, knowing that our K2 value equals 0. So here's my block diagram math that I did to achieve C of S over R of S with combining like terms to get the new transfer function. And I showed the transfer function near the bottom of there. So then we're going to use that transfer function to solve for error later on. So here I just went over the known values that we have. So we've needed to find our overshoot from the Appendix A table. So that corresponds to our birth month and day. So mine's February 1st. So my overshoot is 23.3. Knowing our overshoot value, we can then solve for zeta, which I solved to get 0.42. Knowing those values, I was able to plot my root locus plot by using our transfer function that we solved for with our block diagram math. So I dragged down, found my overshoot value that I was trying to get to, 23.3, to find our gain, our K gain as 3.12. And then I also found pole locations and went through everything that gave me there. From that root locus plot, you can go ahead and calculate the rest of the performance characteristics. So we found zeta, omega d, our poles, and our k. And we know our overshoot already, so you can solve omega n, rise time, and settling time from the equations that we've learned prior. I also wanted to show the calculations for steady-state error by multiplying our transfer function by our k1 and then taking the limit as s goes to infinity. So once we did that, our kp value was 8.214, and then our error equals 1 over 1 plus kp. And so then our error for case A was 0.109. So case A was our baseline. So now we're starting on case B, which we want to solely reduce our steady-state error by 10 while maintaining the same overshoot. So we needed to pick which compensator controller we wanted to achieve that. And by given what we needed, I decided to design a passive lag compensator. That's because its goal is to decrease error while maintaining an overshoot. And by doing that, we have to add in a pole and a 0, which means that our P, which is our pole, has to be less than Z, which is our 0, meaning that our pole has to be closer to the origin. So adding in our lag compensator, we have to do all of our design characteristics now. So we have to solve for our error new, our KP new, and then have to decide where our pole is. So we can solve for our 0, which is ZC, and then I would place those in the standard form, which is K, or which will be our K2, S plus Z over S plus P. And so our GC of S for case B is K2 S plus 0.11 over S plus 0.01. And you can see the work that I did there. So ZC equals PC, and our PC equals 0.01. So I set that equal to what we solved for K new over KP, or KP over K new, to get 11.046. And so then I was able to solve for ZC. From there, we can plot our root locus, do the same process we did to find our new K2, zeta, and pole locations. So after we found our K2 from our root locus and our poles and our zeta, we do the same process again to find our performance characteristics. So for here, I wanted to plot our step functions for case A, which is our baseline uncompensated, which is the blue line, and our lag compensator, which is the red dashed line. So here you can see our rise time and settling time, and then where it will end up going to our error, or steady state error, to get to our steady state. And you can see when we added a lag that it did improve a little bit. So to compare case A and case B, where A was our uncompensated compared to our lag, I just wanted to put them in a table that shows that our overshoot stayed the same and decreased our error, and our performance characteristics adjusted based on those. So case C, we basically did the same thing but with a PI controller, because our objective is to completely eliminate steady state error. And so I added a proportional integral controller because it makes our steady state error 0 by adding a pole and a 0. And the pole needs to be close to the origin, which is part of the system integrator, which pulls an S out. So the bottom is 0. So case 3, I was able to plot my root locus based on where I put my pole. So you can see that I was able to get a close to the same overshoot, and our K3 is 1.22. So then from there, I solved for performance characteristics, did my KC error, which I ended up showing that it did end up reaching a steady state error of 0. Once again, I plotted the two, case A and case C, on the same plot. Here I added a table to kind of show that our error did go from 0.109 in case A to 0 by adding the PI. And then as an overall summary, I wanted to show all of the cases. So case A was my base point, where I compared everything to in order to see how each addition affected the steady state error and characteristic properties. In order to just decrease our steady state error by a factor of 10 and maintain our overshoot, I added a passive lag compensator, which reduced error by adding a pole and 0. And in case C, we wanted to show how the error just went to 0 and was completely eliminated by adding a PI controller. It added a pole near the origin to increase the system type, as it's a proportional integral controller, getting rid of error completely.